Hi everyone, welcome to the Software Development Essentials Workshop and the fourth of 5 total classes. This class focuses on the cloud. Ooh, so mysterious. As always, this class is geared towards the following audience: entrepreneurs who are looking to build a software-backed product, professionals who either already find themselves in the technology space or are looking to break into it, students who are looking to learn some material they might not get in the classroom, and curious individuals who just want to understand more about how the modern world is being built. The objective of today's class is to switch gears and learn about the cloud, the definition, the core philosophies, the various service offerings, security considerations, and pricing models. We will be diving into one of the 3 major cloud service providers today, using Amazon Web Services as a case study. This is our agenda for the day. We're going to first define the cloud, then go over some core tenets that constitute the cloud. We're then going to go over some notable cloud service offerings. Then we're going to see how all of these things get implemented in Amazon Web Services, concluding with an overview of AWS's pricing model. Like the other classes, after the lecture, there will be a quiz waiting for you on the Teachable platform, if that's where you're watching this video. This is another picture of Simba sleeping with a basketball. Ball's life. Alright, so we started talking about this a bit in the last class, but one thing we haven't talked about too much yet is the physical machines that are hosting the databases, or the services, or the applications, or the websites that we're building. No matter what layer of the stack we're talking about, we need physical machines for things to live in and run on. Databases need a place where the tables are created and stored. Services need a place where the code that defines them is run and stored. Web pages need a place where the front-end code that defines them is stored. Applications need a place where the software executables that themselves are run and stored. The physical machines that provide the home for all these things are called servers, computers that serve information to other computers. Put a different way, a server is just a computer but without anyone working behind it at a monitor. If you remember back to class number 2, in which we learned about the internet at a high level, each server within the internet ultimately has a corresponding IP address, which is unique to that server. Every time you use the internet, you are accessing a server somewhere in the world. When you enter a URL into a browser, your computer communicates first with the DNS server that maps URLs to IP addresses, then with the web server that is hosting that website and the front-end components of the web application you're trying to access, which will then communicate with the application server that houses the backend, which ultimately pulls data back from the databases, which could also be on their own separate servers, and ultimately back to your own personal laptop, also a server. Each of these layers needs physical hardware to live in and run on. So before the cloud, if a business needed servers to host anything, they would have them in-house. They would have an IT team that would manage a set of physical servers that the company owned or leased, and that IT team would be responsible for those servers being operational. Whatever tools, applications, software, databases the company needed would be installed onto those servers, which the employees of the company would then have to connect to through a local network to access them, modify them, use them, and interact with them in any way. Additionally, companies that built software would have to vend their own software physically on CDs or other mediums to be installed on the user's machine or set of machines. Think about when, if you're old enough for this, when you had to install Microsoft Word using a disk. The cloud, then, is as simply defined as servers and the software and databases that run on those servers that are accessed over the internet. It's not any more complicated than that. There's no weather involved, nothing related to Cirrus or cumulonimbus clouds. Instead of reaching for your servers on site, you can now reach for them in the cloud, aka through the internet. If you want to visualize this as a cloud still, I sometimes picture it as a server that's evaporating up data to an actual cloud, the cloud carrying it from that server to right above your house, and then that cloud precipitating that data back down to your laptop. By using cloud computing, users and companies don't have to manage their own physical servers or install and run purchased software applications on their own machines. They can just access their servers through the internet with whatever software they need already installed and available, pay for what they use in terms of server capacity, and not worry about anything else. Some examples of how cloud servers can be used: to house your relational databases, to house your non-relational databases, to house and run the code for your large suite of back-end microservices, to store all the images and videos your website uses, to create a private network that all of your other resources live in. The list goes on. Cloud servers themselves are located in data centers all over the world. And just to help explain how massive these data centers can be, in 2020, Amazon bought over 100 acres of land for $73 million in Northern Virginia. That was an expansion on the existing land they already had in Northern Virginia, all to host their largest data center in North America. Amazon has massive data centers all over the world, which ultimately are just massive server farms, which are just huge campuses of buildings that contain rows and rows of servers. The superset of all these data centers represents the cloud. To visualize this a bit, the map on the left here shows all of Amazon's data centers across the globe. The yellow regions are their primary data centers, which are gigantic, and the spots in red are their edge locations, which are a bit more modest and yet larger than anything you're picturing in your mind still. You can see how they are placed strategically in each continent, often for a combination of geographic centrality for the given market and for cost considerations. For example, the primary data center that serves the EU is in Ireland for a combination of cheaper energy resources and tax incentives. The image on the right is what the inside of a single data center might look like. Just rows and rows of servers stacked on top of one another. And the image on the bottom left is just a silly little graphic showing a cloud that is sad that she doesn't actually exist when it comes to what we're referring to as the cloud. No clouds associated with the cloud. Sad cloud. For businesses, switching to cloud computing removes IT costs and overhead. For instance, they no longer need to buy and rent servers. They no longer need to update and maintain those servers, as the cloud vendor they're using will do that for them. They also no longer need to have as large of an IT team, or have an IT team at all. That part kind of sucks when you think about the automation of the workforce and how it leads to people losing jobs, but I don't think the cloud is going anywhere. And the cloud vendors themselves, Amazon, Google, Microsoft, now hire large numbers of IT professionals to help manage their data centers. So it is more of a shift than it is a depletion, which is good. Also, you might still need IT for all the other things related to your company's technology infrastructure, provisioning laptops, office networking, etc. This especially makes an impact for small businesses that may not have been able to afford their own hardware and infrastructure, but can now outsource their infrastructure needs affordably to the cloud. So think of a small startup or a small business that's trying to build some new software. Instead of having to rent physical servers and then having an IT team to help to deal with them, they can just rent some servers over the internet that they don't have to maintain, and they're good to go. The cloud can also make it easier for companies to operate across multiple locations or internationally, because employees and customers can access the same resources from any location. Things are no longer tied to private networks or physical connections to servers. All you need is the internet. Just some more images to help visualize the cloud. The image on the top shows the difference between an on-premise server setup, shown on the right, versus a cloud-based one, shown on the left. One involves on-premise hardware and a local connection to that hardware. The other just involves the internet. And the second image shows that through the internet, you can access remote servers that are in data centers somewhere many miles away to work with your applications and databases. Remember that at the end of the day, everything is just ones and zeros that are being sent and received. The medium of transmission is up to you. The cloud uses the infrastructure of the internet for that medium. Getting into a bit of the nitty-gritty. Cloud computing was made possible because of a technology called virtualization. Virtualization allows for the creation of a simulated, digital-only virtual computer that behaves as if it were a physical computer with its own hardware. The technical term for such a computer is a virtual machine. When properly implemented, virtual machines on the same host server are sandboxed, which means they're kept separate from one another, so they don't interact with each other at all, and the files and applications from one virtual machine aren't visible to the other virtual machines, even though they're on the same physical machine. By running many virtual machines at once on a single physical machine, one server becomes many servers. And that should be the main takeaway from this slide. By sharing the physical machine's resources, the memory, the disk space, etc. And then a data center becomes a whole host of data centers, able to serve many organizations simultaneously. Thus, cloud providers can offer their use of the servers to far more customers at once than they would be able to do otherwise, and they can do so at a low cost. So basically, if it were the case that every physical server were just one computer, the economics of the situation just would render cloud computing exorbitantly expensive and thus infeasible. Virtualization made it so that you can have multiple computers, virtual machines, each which have their own IP address, living in the same physical server. This advancement was instrumental and necessary for cloud computing to even be a thing. So now we're going to get into some of the core philosophies and guarantees of cloud computing. One important tenet of cloud computing, which we'll touch on in more detail later, is that even if individual servers go down, your data in the cloud in general should always be online and accessible. To make this possible, cloud vendors generally back up their services on multiple machines within the same data center and across machines in multiple data centers, thus different geographic locations. So let's say you have a database that's sitting on a virtual machine on a physical machine that is located in a data center in Virginia. If the data center in Virginia experiences a massive power outage or other act of God, which in this day and age is more and more likely, that's okay, since the data has been backed up and is accessible in another virtual machine on another physical machine somewhere in Washington, D.C. This is another big advantage over maintaining your own physical servers. If that same act of God were to wipe out the servers in your office, you'd probably be out of luck. In order to use the cloud, users access cloud services either through a browser or through an app, connecting to the cloud over the internet, regardless of what device that they're using. So if that data center in Virginia does go down, the user wouldn't even be able to tell. They'll request their database resource through the same web portal, and the cloud vendor will now communicate with the backup server in DC to serve the customer the requested content. We're going to get into more of this in a bit. So, just to recap, the cloud is the servers and the software and the databases that run on those servers that are accessed over the internet. Things on servers accessed over the internet, as opposed to things on servers accessed physically on site. But the software and databases part is pretty vague, and there are many options and subsets to cloud offerings that are available for customer use. So what are the main service models of cloud computing? Well, they can be as broad as entire applications that are hosted in the cloud that businesses can access and use, known as SaaS, which stands for Software as a Service. Think about Salesforce or Gmail. Or as narrow as the physical servers themselves that businesses can rent and use for whatever purposes they want, known as IaaS, Infrastructure as a Service. Or the offering can be somewhere in the middle, like getting a server which is already equipped with a DBMS or an operating system, but nothing else. This is known as PaaS, Platform as a Service. At the end of the day, everything is associated with virtual machines living in physical servers that are being utilized in some manner through the internet. But cloud offerings are layered and define the configurations and content of those servers that you're using. The virtual machines can be used empty and thus as blank templates for businesses to use in whatever way they want, or they can be used specifically with something already pre-configured and uploaded for your use case, whether that's a database management system that you want to build or an entirely ready-made application that you just want to use out of the box. So we're going to go through each category of offerings to understand this better. We're going to start with the broadest category and work our way down, called SaaS, or Software as a Service. Software as a Service is a cloud-based method of providing software to users. Instead of users installing an application on their own physical machine through a CD or a flash drive, SaaS applications are hosted on cloud servers and users access that content over the internet. So we're going to use this analogy as we go through each category, so keep it in mind. But SaaS is like renting a fully furnished house. It's already completely livable, has all the amenities and functionality that you'd want. You simply just have to move in and pay rent. The landlord, the cloud vendor, maintains the house and all of its amenities, but the tenant, the user, just pays rent and then gets to use it as if they own it. A SaaS application may be accessed through a browser or an app. The difference between SaaS and a software installation on a user's computer is like the difference between streaming a TV show online and buying all the seasons of the TV show on DVD. Someone who buys a TV show on DVD only needs to pay for it once. However, they will need to store and maintain the DVDs, and if they change their hardware, for instance, if they replace their DVD player with a Blu-ray player, then they'll need to purchase the DVD again on Blu-ray. Streaming the show instead means a third party handles all the storage and upgrades, and all a user needs to do is access the app via the internet and hit play on however many devices they want. However, streaming is dependent on an internet connection, and users typically need to pay a recurring monthly fee to maintain their access to the content. Again, for those of you old enough to remember this, think of how you would need to install applications that were only available on purchased CDs or floppy disks or flash drives, versus how you can just go to a website now and just access an application directly or download it and connect to it through the internet. A prime example of this is Microsoft Office. With Microsoft 365, which is Microsoft's parallel product to Google Suite/Google Docs, anything you can do with Microsoft Office can just be done through a web browser. You don't need to install anything, you just need the internet and an account. Furthermore, the document you create online on your laptop can be accessed through any other device, as long as that device has access to the internet and the account credentials. Examples of other SaaS applications include Salesforce, Dropbox, Gmail, MailChimp, Spotify, Slack, Netflix. The list is endless. Looking at the pros and cons of SaaS versus locally installed software, one advantage is you can access the content from anywhere, on any device. With Office 365 or with Google Docs, I can now create a document on one laptop and immediately access it via my phone or another laptop, assuming I'm using the same account and I have access to the internet. Another advantage is there's no need for updates or installations. Instead of having to buy Office 2020 and 2021 and 2022, Office 365 updates its software on its cloud servers, which is then directly reflected when I access it via the internet. Another advantage is scalability. If I double the size of my company and now 200 people are using Microsoft Office instead of 100, I don't have to worry about doubling the number of computers I maintain in-house with Office software licenses bought and installed. Microsoft Cloud handles all the hardware on its own, based on its total usage and total demand. So maybe now I have to pay a little bit more because my usage has gone up, but other than that, nothing really changes. Another advantage is cost savings. This is a big piece of cloud computing in general, that instead of having to purchase my own servers and the licenses I need to use Microsoft Office on each new device, hire an IT team to maintain those servers, I simply just create a Microsoft 365 account and pay the subscription fee. Some disadvantages. The first one is the need for stronger access control. With SaaS, organizational assets are no longer kept within an internal network separate from the outside world. So whereas previously someone would have to physically break into the office and access one of the servers to access my private Word documents, now anyone who has my username and password across the world can do so. Thus, strong identity verification becomes essential. This is where things like secure passwords, multi-factor authentication, and more come into play and are super important. We'll cover this more in detail later. On a similar note, for enterprise software specifically, security and compliance is another disadvantage. With SaaS applications, the responsibility for protecting the applications themselves and their data moves from an internal IT team to the external SaaS provider. For small and medium-sized businesses, this is less of a disadvantage, as large cloud providers typically have more resources for putting strong security in place. But this can be a challenge if a large business faces tight security or regulatory standards. Essentially, they have to take the external SaaS provider's word that the application is secure. Financial services and banking are two key industries where this is a concern. So on that note, consider a financial services application that is doing the work of consolidating many job functions of an investment manager into a single application. Accounting, trade order management, client management, all done through a single web portal. That'd be pretty great, right? But now an investment management firm, which has kept all of its sensitive financial data in its own servers somewhere secure in the office and complied with many government rules and regulations, as well as built long-standing trust with their customers, has to hand over all this data over to the cloud service provider. Yes, the service provider will make their lives easier, but at what cost? This is a leap of faith that requires lots of communication and trust between client and cloud service provider as to what the standards and expectations are. Assuming the service provider can meet the expectations of the client with strict security requirements, the partnership can exist. Moving on to the next service model. Platform as a Service, PaaS, is a cloud method for providing the necessary tools for building your own software. In this model, companies don't pay for the hosted applications. Instead, they pay for the things they need to build their own applications, hosted on remote servers. PaaS vendors offer everything necessary for building an application, including development tools, database management systems, operating systems, and infrastructure all over the internet. So, going back to the house analogy, PaaS can be compared to renting all the tools, equipment, and raw materials necessary for building your own house, instead of renting the house itself. If you're building your own application, this is the layer of the cloud you'll typically interact with pretty heavily, and is one of the layers your development team will definitely work with. Your house, your application, now needs to get built by your development team, so they will take the tools offered by PaaS and do so. You would use PaaS to build SaaS that other companies or other users will then consume. So PaaS offerings can also be accessed over any internet connection, making it possible to build an entire application through a web browser. Because the development environment is not hosted locally, developers can work on the application from anywhere in the world. This enables teams that are spread out across geographic locations to collaborate. PaaS vastly simplifies web application development. From the developer's perspective, all back-end management takes place behind the scenes, so they can focus more on the quality of the code and the product itself. So diving into some of the specific offerings within PaaS. The first is development tools. PaaS vendors offer a variety of tools that are necessary for software development, including a source code editor, a debugger, a compiler, and other essential tools. These tools may be offered together as a framework. The specific tools offered will depend on the vendor, but PaaS offerings should include everything a developer needs to build their application. The next big one is databases. PaaS providers administer and maintain databases. They'll usually provide developers with a DBMS, a database management system, as well. Operating systems. A PaaS vendor will provide and maintain the operating system that developers work on and that the applications run on. And finally, infrastructure. PaaS is the next layer up from IaaS in the cloud computing service model, and everything included in IaaS is also included in PaaS. A PaaS provider either manages servers, storage, and physical data centers, or purchases them from another IaaS provider. And this is a big one, which we'll dive more into in a second. Different vendors may include other services as well, but these are some of the notable PaaS offerings. So jumping into the pros and cons, PaaS offers a faster time to market. PaaS is used to build applications more quickly than would be possible if developers had to worry about building, configuring, and provisioning their own development platforms and back-end infrastructure. With PaaS, all they need to do is write the code and test the application that they're building, and the cloud vendor handles a lot of the rest. Ease of licensing. PaaS providers handle all licensing for operating systems, development tools, and everything else included in their platform. Things like DBMSs fall under this point. So again, you don't have to buy any of these licenses for yourself. You just pay the cloud vendor. Cost savings. Again, no need to have an IT department or physical servers to house and provision all these things. You can just pay a subscription fee and just pay as you go by usage of what you actually end up using. Some drawbacks though, specifically the security and compliance challenges. In a PaaS architecture, again, the external vendor will store most or all of an application's data, along with hosting its code. In some cases, the vendor may actually store the databases via a further third party, another IaaS provider. Though most PaaS vendors are large companies with strong security in place, this makes it difficult to fully assess and test the security measures protecting the application and its data. In addition, for companies that have to comply with strict data security regulations, verifying the compliance of additional external vendors will add more hurdles to going to market. So again, going back to our financial services example, let's say instead of using a fancy new one-stop shop application, an investment management firm just wants to migrate its financial data from their in-house servers to the cloud, but continue to use their own in-house applications to interact with that data. So they can get a set of virtual machines or servers equipped with whatever databases and DBMS that they need. But again, contingent on that DBMS and that server being able to satisfy the strict security requirements the firm has regarding their customers' sensitive data. So I hope you can see the difference between SaaS and PaaS. SaaS is a cloud-based software that's already built that you or your company want to consume, corporate Gmail or Slack accounts. PaaS, on the other hand, is used by your own development teams to build their own software. That software can be SaaS of its own, but it could also not be. Either way, PaaS is used to build software, so it's in the category that we'll be really diving into deeper along with IaaS. So now moving on to a third category, IaaS, or Infrastructure as a Service. Infrastructure as a Service is a cloud method for providing servers, storage, and networking to users. So it's a subset of PaaS that literally only captures the infrastructure itself. It provides raw servers, raw storage space, and raw networking capabilities. Infrastructure as a Service vendors allow businesses to provision resources on demand and as needed instead of having to buy or rent hardware outright. So again, going back to the analogy, Infrastructure as a Service is like a company leasing or renting a plot of land on which they can build whatever they want. A blank template that is theirs to use as they will, but they need to provide their own building equipment and materials and then decide what they want to do with the space. Infrastructure as a Service is a subset of Platform as a Service. Everything that's included in Infrastructure as a Service is also included in PaaS. And again, your development team will use Infrastructure as a Service and Platform as a Service to build their own software, which maybe could be its own SaaS. Infrastructure as a Service offers many advantages, including it's the most flexible cloud computing model. You can just get the infrastructure you need and then do what you need with it. You can install your own DBMS, applications, storage volumes, whatever. You can choose the specs of the hardware that you get, including the memory, performance, etc., and the rest is up to you. You're just getting blank templates. Scalability. Hardware needs can be based on consumption, and resources can be provisioned as needed. You can get more hardware or less hardware based on your needs, and you can scale up or scale down. So maybe during Christmas, traffic on your application is going to be much higher than normal. So you double the amount of servers that your application is running on just in the month of December. My old team did exactly this. We knew that in Q1, our application experienced much higher traffic than in any other quarter of the year. So we scaled up our hardware just for that quarter and then gave it back once Q2 started. This is touching on a really important topic that we need to address that we haven't explicitly covered yet. The amount of servers or virtual machines you need ultimately depends on the total volume of traffic and load that your application is experiencing. So suppose your application experiences 100 requests per hour at its peak. You need to then provision a corresponding number of virtual machines to be able to handle that load while still providing a positive customer experience in terms of latency. You don't want your customer waiting 30 seconds for your application to load because you only have one virtual machine handling all traffic. In that scenario, the 100 requests would be queued up and the single virtual machine will handle them one at a time. Instead, you want your application replicated across many virtual machines that can share the load of traffic. With 4 virtual machines, each one can handle 25 of the incoming requests. With 10 virtual machines, each one can handle 10. The right number of virtual machines ultimately depends on what guarantees you're making to your customer in terms of latencies. As we covered in class number 2, nearly half of web visitors expect a site to load in 2 seconds or less. So that's a good place to start. And we'll get to this in detail later, but that's an extremely important concept in understanding why the number of virtual machines matters. You use it to distribute load across many servers so as to provide a positive customer experience. Another advantage is still cost savings, again, because you don't have to house these servers in-house and you don't need the associated IT departments to manage them. Are you going to physically lug new servers into your office just for December, or will you inevitably have to keep that number high around the year so as to just satisfy that Christmas load and in turn pay for it year round? Some cons though, Internal resources and training. So additional resources and training may be required for the workforce to learn how to effectively manage their cloud infrastructure. You might not need an IT team anymore to manage physical hardware, but you at least want some part of your workforce to be literate with the cloud hardware that you have. So now all your other past stuff that you're doing in-house needs to be managed by someone internally. Development tools, databases, operating systems. You as the cloud consumer will also be responsible for data security, backup, and business continuity associated with each of these things. So IaaS is way more flexible in how you use it, but in turn, more is required from your employees and your development team. And as always, the security. While you as the customer are in control of the apps, the data, the middleware, and the operating system platform, security threats can still be sourced from the host or other virtual machines. Insider threats or system vulnerabilities may expose data communication between the host and the infrastructure and the VMs to unauthorized entities. So formerly, SaaS, PaaS, and IaaS were the three main models of cloud computing, and essentially all cloud services used to fit into one of these categories. However, in recent years, a fourth model has emerged. But before we jump into it, we need a refresher on microservices. If you remember from the class about the backend, a given application's backend can either exist as a single monolithic service or as a suite of microservices. Right? So on the left-hand side, we see our single service, let's call it the Save the World service, which has all of the functions associated with saving the world built into a single monolithic service. That service is then housed in its entirety across multiple servers to handle and distribute request load. Alternatively, each function of the application, let's call them the redistribution of wealth service, the addressing climate change service, the criminal justice reform service, the equal pay service, the love is love service, the education reform service, the arts service, etc., can each be its own separate service. That's the microservices approach. So the redistribution of wealth service, addressing climate change service, equal pay service can each be housed separately across servers. And maybe the addressing climate change service, the yellow block, is replicated 5 times, but the green blob, the redistribution of wealth service, is only replicated 3 times, because the addressing climate change service part of the application gets used more than the redistribution of wealth part does. So again, this approach of building an application out of a set of modular components is known as the microservices architecture. Dividing an application into microservices is appealing to developers because it means they can create and modify small pieces of code which can be easily implemented into their code bases. This is in contrast to monolithic architecture, in which all the code is interwoven into one large system. With large monolithic systems, even a minor change to one part of the application requires the entire thing to be changed and redeployed. So this is where we introduced Functions as a Service, or FaaS. FaaS, also known as serverless computing, breaks cloud applications down into smaller components that only run when they're needed. FaaS still run on servers even though we call it serverless, as do all of these models of cloud computing. But they're called serverless because they don't run on dedicated machines, and because the companies building the applications don't have to provision any servers explicitly. Serverless functions scale up or provision hardware as people use the function. So prior to FaaS, if you wanted to host your suite of microservices, you would provision some servers, infrastructure as a service, and upload your microservices to these servers. They would live and run on these servers, sitting idle potentially, and would be available when they were needed. This would be true regardless of if you had a monolithic service or a set of microservices. Now, instead of renting these dedicated machines virtually to put your microservices on, there's just a massive pool of hardware that is shared by every cloud customer and every use case that's out there. And that hardware is borrowed and returned as it's needed in real time, instead of always being allocated and designated for any one customer's uses. So imagine if it were possible to pay rent on various plots of land only as they are used. Maybe it's a big polo field in the middle of a desert somewhere in California. Sometimes it's used for large music festivals, sometimes it's used for the world's largest farmers market, etc. So now when you need to host an event, you pay the grounds owner and use it for just that time period, and then when you're done, you stop paying, and that land can be used for something else. That's how serverless computing works, except replace the event organizer with a cloud customer and the plots of land as a server that you can rent to host your microservice. Going even further with this analogy, serverless functions can scale up or provision extra hardware if more people use the application than anticipated. So imagine if the events organizer could rent more plots of land on demand when more people show up to see Beyonce's legendary 2018 set than originally expected. So now, instead of having to provision as many servers as your max use case at all times, which would be paying rent on the plots of land year long for an event that only happens 2 weeks of the year, you get as many servers as you think you need, only when you need them, paying just for the weekends that the event is happening and being able to get more land if you need it on the weekend itself. So taking this back to our Save the World application, if the equal pay service was used much more often than the art service, it would just be replicated onto new servers in real time as it was being called, while the art service wouldn't. Notice how this wouldn't be possible with a monolithic approach? In that approach, since the equal pay service and the art service were tied together, the entire monolith would have to be replicated based on the maximum call rate across all the services. I hope you can see how wasteful that is. So let's keep diving into this. Let's say you have a Say Their Names service as its own microservice, which has its own separate database of all the names of innocent black folks murdered by police officers, as does the Redistribution of Wealth service, which shows how the majority of the wealth in the world belongs to a smaller and smaller percentage of the global population, and how many issues that this leads to. You then have a third parent microservice, which just combines the data from these two microservices and populates the HTML to be returned to the user. Now, using the standard IaaS model, you would need to provision as many virtual machines or hosts as is required by your most used microservice. So, if the Say Their Name service part of the application were used once an hour, and the Redistribution of Wealth part of the application were used 10 times an hour, you would want to provision a number of hosts according to the 10 times an hour rate, and then replicate the Redistribution of Wealth microservice across all these hosts, and maybe just have the Say Their Name service part of the application on only a few of them. With the serverless compute model through FAST, you can bypass all of this and not provision any hosts at all. You just upload your code for each microservice, which will sit idle until the cloud provider needs to provision hardware in real time based on the requests that are coming in. So that's what this graph shows, and how this ultimately translates in terms of efficiency is cost. The overall amount of code and data that is replicated is drastically reduced, and your microservices are never sitting idle, and thus your costs associated with the replication and storage of them is drastically reduced. So don't get stuck too much into this graph yet, since we'll come back to it, but just understand that the area under each curve here is your total cost associated with each model. And by matching the demand more explicitly in real time to the actual provisioning of whatever hardware that you're using, you are minimizing the area under that curve and thus minimizing your costs. So I promise we'll get back to this graph more, but that's at a high level what's happening. For now, just remember the basic concept of how FAST takes cloud computing one step further. Instead of provisioning dedicated cloud servers for your microservices, you don't have to worry about provisioning servers at all. Just upload your code, and your servers will magically appear when they're needed, and then be returned to the shared pool when they're not. So again, developers no longer have to worry about how many servers they need to host their services. They simply just write their code as a suite of microservices and upload it to the FAST provider. The FAST provider will then worry about how to provision the hardware to house those microservices as and when they're required. This literally means that instead of an application just living constantly on a set of hosts that you provisioned via the infrastructure as a service model, where your monolithic application or your suite of microservices lives constantly on designated sets of rented servers, and then one of those servers responds when requests reach it, and then those servers will sit idle when there's no requests coming in. As opposed to that, now a developer will just upload a microservice as a code packet to their cloud provider, Then, when a user of the application requests say their name's data, the FAST provider will find an available server in its massive shared arsenal, set it up, upload the say their name service to that server, run it, return a response to the customer, tear that server back down, and then add it back to the arsenal. So again, serverless just means that there are no dedicated hosts being used. Hosts are pulled from a common pool only when they're needed based on the requests that are coming in. The cost savings from this can be quite significant. So you shift from paying for cloud servers 24/7 to only paying for servers when they're actually needed in real time. So what are the advantages of using FAST? Well, one is improved developer velocity, right? With FAST, developers can spend more time writing application logic and less time worrying about servers and deploying and managing the infrastructure. Another is built-in scalability. Since FAST code is inherently scalable, developers don't have to worry about creating contingencies for high traffic or heavy use. The serverless provider will handle all the scaling concerns. So going back to the Christmas example, if your application sees 10x the load on Christmas Day than it normally does, you don't have to worry about provisioning 10 times the host to handle that load. The day of, the hour of, the minute of, when your services start seeing a ridiculous amount of load, the FAST provider will just take care of it. They'll see, okay, we have a lot more load, we have this massive shared pool, we need to pull that many more hosts to serve these requests. Cost efficiency. So unlike traditional cloud providers, serverless FAST providers do not charge their clients for idle computation time. So if your application is not being used, your services are just sitting there doing nothing, which is wasteful. Because of this, clients only pay for as much computation time as they use and do not need to waste money over provisioning cloud resources. Some drawbacks though. With FAST, you get less system control. Having a third party manage part of the infrastructure makes it tough to understand the whole system and adds some debugging challenges. And another big one is more complexity required for testing. So because you don't actually have access to the servers that your code is running on, it can be very difficult to incorporate FAST code into a local testing environment, making thorough testing of an application a bit more intensive. But there's definitely workarounds to that. So before we jump into AWS, just want to do a recap of the cloud. So the cloud is just a remote set of servers that are being utilized for various purposes. SaaS, software as a service, provides software on a remote set of servers that are ready to use out of the box. Examples include Gmail, Slack, Spotify, etc. Platform as a service, PaaS, provides the necessary tools for building an application that you would use to build your own software. This includes servers preloaded with DBMSs or an entire suite of developer tools. Infrastructure as a service provides servers, storage, and networking. In other words, the infrastructure needed to build an application. We'll touch more on the storage and networking later, but with the servers themselves, you're just getting raw servers with nothing pre-existing on them. They're blank templates for you to use as you will, perhaps to upload your suite of microservices, your databases, your static images, whatever you want, you can upload to. Alternatively, you can use FAST, functions as a service, which break cloud applications down into smaller components that only run when they're needed through a serverless model. Now, instead of renting a bunch of blank template servers and uploading your services to them, you can just upload code to a FAST provider, which will then provision servers from a shared pool as and when the services receive user requests. Your development team will use a combination of infrastructure as a service, platform as a service, and functions as a service to build software. Imagine using FAST to upload your suite of microservices, PaaS to provision servers to host all your data in relational databases, and infrastructure as a service to provision servers to host the file systems and object storage locations where all your static content, such as images, videos, and etc., live. This would be a pretty neat architecture for a brand new application. Alternatively, your company will probably use SaaS in other business contexts outside of development. Salesforce to manage client data, Slack for internal communications, Gmail for your internal email server. But you typically won't use SaaS to build your software. So now that we understand what the cloud is and how vendors can offer various flavors of cloud offerings to businesses, let's jump into one particular cloud vendor that does it all: Amazon Web Services, known commonly as AWS. AWS is a comprehensive, evolving cloud computing platform provided by Amazon that includes a mixture of infrastructure as a service, platform as a service, packaged software as a service, and fast functions as a service offerings. It's comprehensive because it's a one-stop shop for cloud services across the types of service offerings, and it's continually evolving because there are still new services being added every single year. AWS launched in 2006 from the internal infrastructure that Amazon.com built to handle its online retail operations, and it's arguably one of the most genius business ideas of all time. They basically took what they did internally to build out Amazon.com and started selling it as a method of building applications. My old team at Amazon, shout out Broadway team, was entirely built on a suite of AWS technologies. AWS was one of the first companies to introduce a pay-as-you-go cloud computing model that scales to provide users with compute, storage, or throughput as needed. AWS offers many different tools and solutions for enterprises and software developers that can be used in data centers in up to 190 countries. Groups such as government agencies, education institutions, nonprofits, and private organizations can use AWS services. Some of the biggest spenders on AWS are Netflix, Twitch, LinkedIn, Facebook, ESPN, and Twitter, and many, many more. Its net sales were $25.5 billion in 2019, and Contino's 2020 research report, The State of the Public Cloud and the Enterprise, shows that a whopping 64% of enterprises who are in the cloud in some capacity use AWS. How AWS works is that it is separated into many different services, all accessible through the same single web portal. Each one can be configured in different ways based on the user's needs. Users are given configuration options and individual server maps depending on the AWS service being used. More than 100 services comprise the AWS portfolio, including those for compute, for database management, infrastructure management, monitoring, analytics, and security. These services by category include compute power, which is just raw servers being used for their resources, database management, which we all know is the storing of databases and the access to the DBMS that you need, object storage, this is the equivalent of a cloud-based hard drive, networking, this we'll get to more later, but it's creating a range of IP addresses in the cloud that you control. Development tools is an example of a cloud-based code editor where you can write code and save it to the cloud. Monitoring and analytics, this is being able to see how your application is performing. Security, this is a huge part of the cloud because, as we discussed in previous slides, moving to the cloud is a security risk. The services the cloud provides to ensure your data and applications are secure are very important, and AWS does a great job of that. And messages, which allows your applications to send and receive messages. You can see here each category is broken out into its type of offering, and you can see that all offerings are covered. And fast isn't here, but that's also covered. So before we jump into some of the notable service offerings in AWS, we need to first cover a few important concepts. First off, let's start with high availability, which means that a system generally is accessible and functioning with minimal downtime. AWS infrastructure, the way their data centers are set up, and the way in which virtual machines are provisioned provide ways to ensure a highly available system. We talked about this briefly before as a general concept within the cloud. Replicating your stuff across many servers can provide high availability. If one server goes down, that's okay, you have backups. Taking this a step further is fault tolerance, which means that a system generally is functioning and accessible with zero downtime. So not minimal downtime, zero downtime. This is saying that even if an entire geographic area of servers goes down, that's okay. So again, AWS provides the infrastructure to ensure a fault-tolerant system as well. But it's important to note that this is often associated with a higher cost, since you have to provision a more sophisticated system to ensure fault tolerance across multiple geographic locations. The next important concept is scalability, which is the ability of the system to add resources to accommodate expected changes in demand. This is used to satisfy long-term strategic needs. So again, An important concept that I want to keep addressing is that a given server can only handle a certain amount of load measured in requests. Similar to how your brain can only handle a finite number of tasks or trains of thought at a given time, a server has that limit too. Based on the demand you anticipate, you would provision the appropriate amount of servers to satisfy that demand. So let's say you used AWS to provision 10 servers in the cloud to host your new retail website selling various trinkets and gizmos. You realize at the start of December that during the holiday season you expect the demand on your website to double, and the 10 servers you have aren't enough to handle that additional demand. With the click of a few buttons, you can provision 10 new servers for the month of December and then give them back again in January once that demand returns to normal. That's scalability. Elasticity, on the other hand, is the ability to fit the resources needed to cope with loads dynamically to address unexpected changes in the demand. Elasticity is used to satisfy short-term tactical needs. The example here would be if your retail website was selling a gizmo that Barack Obama tweeted about at 1 p.m. All of a sudden, your website saw a massive spike in demand for this gizmo. An elastic system would be able to dynamically scale up the amount of servers to handle this spike, and then scale back down when the spike has subsided. AWS provides configuration options to make this possible. So to recap, AWS provides options to build a highly available, fault-tolerant, scalable, and elastic system. But how does AWS accomplish this? How does it provide high availability and fault tolerance, for example? Well, for those two, it provides it through concepts known as AWS regions and AWS availability zones. AWS provides services from dozens of data centers that are spread across availability zones in regions across the world. An availability zone, known as an AZ, is a physical location that contains physical data centers with physical machines that host your virtual machines. A region is a collection of multiple availability zones in geographic proximity connected by low latency network links. Examples of regions are Northern Virginia, Ohio, and Oregon. So within the Northern Virginia region, there are multiple availability zones which represent like the data centers themselves. So the Northern Virginia region could have 3 availability zones, each of which is a massive server farm. A business will choose between one or multiple availability zones within a single or across multiple regions when using or deploying a given service to ensure high availability or fault tolerance. We'll get into an example between a highly available system and a fault-tolerant system in just a minute. The map on the left here shows all of AWS's regions across the world. Within each region, there are a handful of availability zones, which again are just the massive warehouse compounds that are filled with servers. And a given warehouse compound filled with servers might look like the image on the top right. So now let's jump into some of the notable service offerings on AWS. Going back to our house analogy, the most flexible model of cloud computing, infrastructure as a service, offers the servers themselves without any applications already on them, which would be SaaS, or without any of the platform tools already available on them, which would be PaaS. Blank templates, plots of land that you can build whatever you want on. So the service in AWS that offers servers is called EC2. Amazon Elastic Cloud Compute, EC2, is one of the most used and most basic services in AWS. And just to give you an idea of how widely used EC2 is, Netflix spends 19 million, Twitch spends 15 million, LinkedIn spends 13 million, and Facebook spends 11 million on EC2 servers monthly. Netflix uses more than 100,000 EC2 instances on AWS for nearly all of its computing and storage needs. This includes the databases, the analytics that they run, the recommendation engines that they have, as well as the video transcodings themselves. EC2 is used to provision a virtual machine on a physical server with the operating system and hardware components of your choice. So again, to caveat here, when you provision an EC2 instance, as they're called, you're not getting a full physical server. You're getting a single virtual machine on a physical server. Remember, virtualization made it possible for one physical server to become many servers. And so virtual machines is the granularity that customers request cloud capacity in. If it's easier for you to visualize this though, you can just keep thinking of it as a separate physical computer. As we already know about the benefits of infrastructure as a service generally, Amazon EC2 instances, as they're called, eliminate the upfront investment in physical hardware. There's no need to have servers in-house and no need to have an IT team to manage them. Additionally, EC2 provides both scalability, which means you can request additional virtual machines when you need, and elasticity, which means that your instances can be configured to dynamically scale up or down with traffic. So taking a look at some screenshots of provisioning EC2 instances from the AWS Management Console that you access through the internet. In step 1, you can see options to select the AMI, the Amazon Machine Image, which is the software platform for the instances that you're provisioning. You can choose from Windows, Linux, Macs, Ubuntu, or the default Amazon AMI, which is Amazon Linux. Next, you would select the instance types. You get options on the type of core, the number of CPUs, the memory, the storage space, the network performance. This is selecting the hardware specifications of your virtual machine. Next, you would configure the instances. You choose how many instances with the previously selected configurations you want. You would configure the storage volumes, the security groups, the network into which this instance will be launched, and more. And finally, you'd review your selections and launch the instance. You can access the instances in a number of ways, but we're not going to get into those technical details today. In terms of nomenclature, when you hear servers or hosts or instances, we're talking about the same thing. It's a place that you put things in. Moving on to another infrastructure as a service for storage, which is actually even more granular than EC2, EBS, known as Elastic Block Storage. EBS provides block-level storage volumes, either HDD or SSD, for persistent data storage. A volume is a device that works like a hard drive. So now, instead of provisioning a full host, you're now just provisioning a hard drive. You don't need the compute power of the machine, you just need the space. EBS volumes, parallel to EC2 instances, work like hard drives that can store any type of data, including file systems, transactional data, databases, and applications. When you provision an EBS volume, the data that is stored in that volume is automatically replicated across multiple EC2 instances running in a single availability zone. This provides high availability. So you create an EBS volume, which now lives on some EC2 instance, and EBS as a service automatically backs it up to another instance within the same availability zone. Another cool thing with an EBS volume is that once it's created, it can be mounted in an EC2 instance easily. So let's say you provision an EBS volume, but then you realize you need an actual EC2 instance to run something else using the data that's on your EBS volume. Now you can provision an EC2 instance separately and select your already existing EBS volume to be mounted onto that instance. It's virtual Legos. Things can be created independently and then joined together. When configuring an EBS volume, you can see that you can select what type of hard drive you want, the size of the hard drive, the primary availability zone in which it exists, whether or not the data should be encrypted, and more. Again, all of this with a few clicks through the AWS web interface. But let's take a pause here because this is an important fork. EBS is a service in which you no longer worry about what server or virtual machine the volume you're provisioning lives on. All you need to know is that it's somewhere in the availability zone that you select and that it has been replicated to another server somewhere in the same availability zone. This is different from an EC2 instance. You provision an EC2 instance which has a specific IP address that is mapped to it that then you can use to access that instance. If the physical server holding that virtual machine burns to the ground, whatever was on that EC2 instance is lost unless it was backed up. So if you were smart enough to have multiple EC2 instances with backups enabled, you'd be safe. So just remember, despite the fact that EBS volumes are more granular by nature of them being a subset of what an actual EC2 instance offers, EC2 instances in their entirety leave a lot more up to you, the user. EC2 is the most flexible of the AWS services. Something like EBS, on the other hand, which again acts more like a service, takes care of things like data replication on your behalf behind the scenes, and you don't really care about the host that it lives in. This is kind of similar to the FAST model that we discussed before. The host itself is kept hidden from the user since it doesn't matter, except now instead of uploading your microservices, you're uploading images or files onto a volume, and you don't really care where that volume lives. Other AWS services will also do a lot of things on your behalf and build on top of EC2 without you necessarily knowing or caring about the EC2 instances themselves. Whereas using EC2 directly means you do care about the specific virtual machines and you are thus responsible for them. Moving on to another service that will continue highlighting this, Amazon S3 stands for Simple Storage Service, which provides scalable object storage for data backup, collection, and analytics. An S3 bucket, again, a term analogous to an EBS volume or an EC2 instance, basically just defines the most granular entity you provision within a given service. So within S3, you provision a bucket. Within an EBS, you provision a volume. Within EC2, you provision an instance. And an S3 bucket is used to store data and files as S3 objects, which can range up to 5 gigabytes each. Data in S3 buckets are replicated across multiple instances and across multiple AZs. This provides high availability and fault tolerance. You can see the difference. So in our EBS example, one server goes down, which has our EBS volume in it. That's okay because we have the data backed up on another server within that availability zone. But what if the entire availability zone goes down? Now you're out of luck in the EBS world. But with S3, even in that case, you'd be fine because your data has been backed up to another availability zone in that region, which remember is another geographic location. An S3 bucket can store a virtually unlimited number of objects and is often used to store static content such as front-end code for HTML, JavaScript, and CSS. When configuring an S3 bucket, you're no longer worrying about space or even the type of hard drive. All you're doing is selecting a name for your bucket and a region for that bucket to live in. AWS takes care of everything else on its own as that bucket gets used. So AWS has its own section of its massive server farm dedicated to S3, which has all the servers that are used to host all the S3 objects in the world. You as the user have no insight into where exactly your data lives, but you don't care as long as you're guaranteed for it to be there when you need it. So between EBS and S3, which are two storage services, there's a number of notable differences. From a pricing standpoint, EBS is you pay for what you provision in terms of the total space you request when you provision a volume, whereas S3 is pay for what you use in terms of how many objects are stored within a bucket and how frequently those objects get accessed. From a scalability standpoint, if you provision a 100 gigabyte EBS volume, you can manually increase its size if you find you need to. But with S3, you don't have to worry about that. Just keep adding to your bucket and AWS will take care of the rest behind the scenes. The only restriction is that each individual object can only be maximum of 5 gigs in size. From an availability standpoint, we discussed this, EBS automatically replicates data across multiple hosts in the same AZ, whereas S3 does that and replicates the data across multiple AZs. Highly available versus fault tolerant. There's some performance differences as well, but ultimately it'll come down to your specific use case to determine which storage service makes sense for you. If you have an ever-growing data set that you know won't have any objects that are too large, just use S3 and pay for exactly what you end up using. But if you have a known set of data that's maybe a database or some other boot volume, use EBS. AWS offers both solutions as well as one other type, EFS, which is Elastic File System, that we're not going to get into here. But you have options. Continuing on in the space of infrastructure as a service, let's shift to networking. Networks are part of infrastructure and are therefore considered part of IaaS. So now we need a quick recap from class number 2, where we learned about how the internet works. Remember that when you type in www.google.com into your web browser and hit enter, the first step that happens is your browser communicates with a DNS server, which translates that domain name into the IP address of the web server corresponding to that domain. That's the server where your HTTP request will be sent, and from which your HTML response will be received. So in simple terms, a DNS server converts World Wide Web addresses like www.google.com to IP addresses like 10.20.30.40. So enter Amazon Route 53, which is a domain name system which translates domain names into IP addresses to direct traffic to your website. Remember that DNS is a distributed system. Domain queries are automatically routed to the nearest DNS server to provide the quickest possible response. Route 53 is built using AWS's highly available and fault-tolerant infrastructure, so DNS servers are distributed across many availability zones. You would use Route 53 to do the following. 1. Register a domain name, such as www.example.com. 2. Create an Amazon S3 bucket and configure it to host that website. 3. Create a sample website and save the files associated with that website in your S3 bucket. 4. Configure Amazon Route 53 to route traffic to your new website. So now, whenever a user goes to www.example.com, they'll be routed to your new website, which will pull the HTML content from the S3 bucket that you created. So you can see how Route 53 and S3 are connected. Another service to mention quickly here is Amazon CloudFront, which is a web service that speeds up the distribution of static and dynamic web content, such as HTML, CSS, JavaScript, and image files to the end users. CloudFront delivers content through a worldwide network of smaller data centers called edge locations. When a user requests content that is being served through CloudFront, the request is routed to the edge location that provides the lowest latency, fastest speed. So, instead of your HTML sitting in a specific availability zone and then always being fetched from that availability zone as requests come in, CloudFront will take that HTML and keep it in a bunch of different edge locations. Based on where a given request is coming in from, it'll be served from the closest edge location. Remember, transferring zeros and ones from Virginia to New Jersey takes longer than from Staten Island to New Jersey. So it's little innovations like this that make AWS the continued leader in this space. Right? We're talking about milliseconds of improvement, but still significant when it comes to application performance. So CloudFront can be visualized as a really efficient web server that sits between the client and the backend. It will serve up content as quickly as possible from an edge location that is closest. So in these two images, I tried to line up vertically where you can picture CloudFront. Again, think of it as the web server or the front door to your application. If your website is static and very simple, let's say it doesn't have any databases or microservices at all, so it doesn't really require an application server. It's just a site with a picture of a cat on it, or maybe isit2021yet.com, which is just yes or no, static, unchanging content. If that's the case, with just 3 AWS services, Route 53, CloudFront, and S3, you can host your entire website. S3 is where you would store the unchanging HTML, JavaScript, and CSS files for your cat page. Route 53 is where you would register the domain of www.mycatisdope.com and point it to your S3 bucket. And CloudFront is what would fetch the static content from S3 and return it to the user in an HTTP response whenever an HTTP request comes in, using the edge locations to distribute the content from the S3 bucket around the area. We'll come back to this in a bit and with a larger example, since most applications aren't as simple as this and often do need an application server and a backend. But hopefully you can start to visualize how the various pieces of AWS service offerings can be tied together. Moving on to another infrastructure as a service offering, the Virtual Private Cloud. Virtual Private Cloud, known as VPC, is a service that enables users to launch AWS resources, such as instances, into a virtual network that they define. A VPC lets you use any of the services offered by AWS in a logically isolated space within the AWS cloud. So the VPC itself, in simplest terms, is a range of IP addresses that defines the boundaries of the VPC. Subnets are subsets of this IP address range, allowing the user to create public and private divisions within the VPC. IP addresses in the public subnet can be accessed by anyone through the internet, whereas IP addresses in the private ones need to pass additional security thresholds in order to get in. A VPC provides an additional layer of security for all AWS services that you use. It gives you full control over routing traffic to and from your instances. All your instances across the AWS services that you used can be deployed into your VPC. You can launch AWS resources into a specified subnet. You can use a public subnet for the resources that must be connected to the internet, and a private subnet for resources that won't be connected to the internet. So here's a quick visualization of a VPC. You've used Route 53 to map www.mycatisdope to an IP address that is part of your VPC's public subnet range. A request comes in from the internet to that IP address. The router determines which subnet to route that request to. Accordingly, one of the EC2 hosts in your VPC will be hit by the request, assuming the request has the proper security credentials to enter the subnet. It'll then do whatever it needs to, return the response, and that'll get served back to the user outside of the VPC. Here you can see the page to create a VPC, where you just basically choose a name for your VPC and the availability zone that it will exist in. And then, going back to step 3 of provisioning an EC2 instance, you can see the page where you specify which VPC you want to launch the EC2 instance into. VPCs are really important as a first layer of defense between the internet and all of your AWS resources. By specifying who is or isn't allowed into your IP subnets, you can make sure only authorized users are making their way in. If you're confused at this point about how all these things are connected, that's okay. We're covering each individual service individually first, and we'll continue to get more into the integration as we go on. I know this is a lot. So let's move out of the world of infrastructure as a service and move into the world of platform as a service, PaaS. And let's start with one of the most common and widely used PaaS offerings, databases. If you remember from last class, items in a relational database are organized as a set of tables with columns and rows. An RDBMS, or Relational Database Management System, is a DBMS designed specifically for relational databases. It's the software that executes queries on the data, including adding, updating, and searching for values. RDBMS is the most popular DBMS in the market. Examples include MySQL, Oracle, and Microsoft SQL Server. So in the AWS ecosystem, RDS is the primary service offering for relational databases in the cloud. Amazon RDS provides database connectivity through the internet to set up a relational database in the cloud. RDS is a fully managed RDBMS service and has many RDBMS options, including Amazon Aurora, Postgres, MySQL, Oracle Database, and Microsoft SQL Server. Amazon Aurora is an in-house AWS RDBMS that provides performance 5 times faster than a traditional MySQL database and 3 times faster than a traditional Postgres database. So this is another thing that Amazon does. It'll support other vendors, but then it'll also build its own competitor version where it can. If you know something like Amazon Basics, something like this, it's like the Amazon Basics, but for cloud services. And finally, another thing to mention is the AWS Migration Hub provides tools to migrate databases from in-house that you already have to AWS. So let's say you have a bunch of databases in your on-premise servers. AWS has a service to help you just move those into the cloud seamlessly. When configuring an RDS instance, you're first selecting a DBMS engine. You can see MySQL, Amazon Aurora, Oracle, and Microsoft SQL Server all as options. You would also select the type of EC2 instance that your database would live on, whether or not you want the database to be replicated across multiple AZs for fault tolerance, and specify the VPC that the database will be deployed into, along with some other settings. When you hit Create, you now have access to a relational database in the cloud that you can upload data to in a few simple clicks. I hope you're starting to see the value prop of the cloud. Think of the alternative. Buy a server, install a DBMS onto that server, connect to that server, download some client you need to use for the DBMS that you installed, and then be able to create and interact with the relational databases, as opposed to going to a website, clicking a few buttons, and accessing a relational database in the cloud that you only pay for based on what you use. Staying on the topic of databases, let's move away from relational databases into non-relational databases. If you remember, non-relational or NoSQL databases are schema agnostic and can exist in multiple forms, such as key-value databases, document databases, search databases, columnar databases, and graph databases. DynamoDB, otherwise known as DDB, provides database connectivity through the internet to set up a non-relational database in the cloud. So RDS is for relational, Dynamo is getting now into the non-relational database management world. DDB is a fully managed NoSQL database management service for key value and document databases specifically. Data must be non-relational and schema agnostic. DynamoDB is serverless. Serverless applications still run on servers as we discussed with the fast model, but they don't run on dedicated machines. There are no EC2 instances that are provisioned to host your databases. So let's pause here and again really key in on this word serverless. We've seen it before when discussing fast and with S3, but we need to really understand. We make sure that we know what we're talking about here. DynamoDB is serverless in the same way that S3 is serverless. Serverless simply means that we don't care about which specific servers these tables live on, and hence we don't have visibility into those details. As long as we can access the data when we need to, we're good. AWS takes care of the rest behind the scenes. RDS, on the other hand, required us to select the specifications of the EC2 instances that the RDBMS and databases would exist on. Since DynamoDB is schemaless and non-relational, it's more elastic. It will grow and shrink hardware needs dynamically depending on the content of the table and how it's accessed, similar to how S3 is elastic based on the contents of the bucket and how it's accessed. DynamoDB can handle more than 10 trillion requests per day and can support peaks of more than 20 million requests per second. So you don't have to worry about being able to access your data in optimal times. So if you remember, for both key value and document databases, the only thing that was mandatory was that there was a key that would be used to access the value space. In light of that, creating a DynamoDB table simply requires a name for the table and a key. That's it. And then you hit create, and you have access to an extremely large NoSQL database in the cloud. 2 clicks, 2 fields. It's that easy. Another AWS offering of non-relational databases that we're not covering in detail is the Elasticsearch service, which is an AWS service that provides a search database engine in the cloud. Moving along to one of the coolest services I think that AWS offers in the form of FAS. It's called AWS Lambda. Lambda is a serverless compute service that lets you run back-end code without provisioning or managing servers. Functions are uploaded to Lambda, after which Lambda automatically allocates instances to run your code based on the incoming request volume. Lambda is the AWS service that allows you to implement a microservices architecture for your back-end services. So each microservice is written as a Lambda function. And Lambda functions can be written in many programming languages: Node.js, Python, Go, Java, etc. So again, going back to our example from before, let's say you have a love is love service, which shows all the different beautiful ways in which two human beings can fall in love, as its own microservice, which interacts with its own separate database in RDS, as does the education reform service, which provides recommendations as to how our public education system can be improved and revitalized. And now you also have an infrastructure and manufacturing service along with its own database, and maybe this one is non-relational and lives in DynamoDB. You then have 2 parent microservices that organize the microservices below it, which then ultimately interact with the user interface and the client. Now, using the standard infrastructure as a service model, you would need to provision as many virtual machines as is required by your most used microservice. So if the education reform part of the application were used once an hour, and the love is love part of the application were used 10 times an hour, and the infrastructure and manufacturing part was used 3 times an hour, you would want to provision a number of EC2 instances according to the 10 times per hour rate and replicate the love is love microservice across all those instances. And then maybe you have the infrastructure and manufacturing and education reform microservices on only a few of them. Whatever parent my microservice was using the love is love service would also have to be replicated across all the instances, because it would have to be called in order for the love is love service to be called. So it's got to match. With the serverless compute model, throw all this confusion out the window, and you don't have to provision any instances. All you do is upload the code for each microservice to its own Lambda function, and then AWS will provision the hardware that it needs in real time as requests come in. Lambdas can reference other Lambdas, and they can also interact with all the other AWS services. So if your Lambda needs to interact with data that's in RDS or Dynamo or S3, no problem. Just add that logic in the code in the function that you upload, and it works together like magic. Lambda is the connective tissue across AWS services. It's how you build workflows and processes and algorithms that connect different AWS services together. Read from a database in RDS, then run some business logic on that data, then join that data with some other data from DynamoDB, then fetch an HTML template from S3 along with some other static content, join it together, return the HTML response back to the user. Lambda functions make all of this possible, and they're super dope. So when you're creating a Lambda, you just need to name it, provide it with a runtime, which specifies the language that it's written in, and thus the compiler that needs to be on the machine that this code ultimately runs on. It's not visible to the user. And then the code that represents the content of the Lambda function. Then you upload it, don't worry about the hardware, and watch it run. As requests come in, AWS will upload your code to EC2 instances behind the scenes and execute the logic that exists within your function. Once the logic is done running and your function is completed, it'll remove your code from the instance and clean up. The amount of instances your code lives on depends on the request volume coming in. It's all dynamic, which in turn means it's also very cost efficient. But again, more on the pricing stuff later. Another service worth mentioning when discussing FAS and Lambdas is something called Amazon API Gateway, which is a fully managed service which makes it easy for developers to maintain, monitor, and secure a suite of microservices at any scale. API Gateway acts as the front door for the application's backend when a request needs to access data, business logic, or any functionality from backend services. So when API Gateway receives a request from a web server for some additional data, again, talking about a more complicated website than a cat one, where data needs to be fetched from databases and services need to be executed to run business logic. So when a request comes in from a web server to what is now the backend, the API Gateway consults a routing map that has been configured that specifies which service to route the request to based on what is being requested, and then sends the request along to that service. When it receives a response back from the service, it then forwards that response back to the web server. So the easiest way to visualize this is this image, which just shows how the API Gateway sits in front of your suite of Lambda functions, and based on the information being requested, love is love data, or education reform data, or infrastructure manufacturing data, it'll route the request along to the proper Lambda function. All right, so I know that was a lot, and so this is the really important slide where we're going to try and tie it all together. So here we see the architecture of a web application that's completely hosted in AWS. You've set up www.savetheworld.com, and you've used Route 53 to register that domain with your AWS hosted application. So user enters www.savetheworld.com in the browser, and Route 53 tells them that this maps to this particular place, and the request then gets routed to your CloudFront distribution, which again, you can think of the web server, the front door into your application. For static content of your website, that's your front-end code, the JavaScript, CSS, and HTML frames, you've stored these things in an Amazon S3 bucket. So the CloudFront distribution will fetch your front-end code from there, which represents the website itself. But the shell of your front-end code now needs to be populated with the dynamic content based on the request coming in, maybe for a specific client or account or whatever else. So now we get to the back end. Here, we'll see an Amazon API gateway, which again is the front door to your back end and serves as the router to your services. It contains a map, which maps type of request to the service that responds to that type of request. If the request is for the Love is Love information or the climate change information, API Gateway will be configured to find the correct service. One thing to mention is that API Gateway can route to Lambdas, but if you're building a service and hosting it yourself in a set of designated EC2 hosts for some reason, it can route there as well, which I illustrated in the middle there, just to show you both cases. So in the top one, we have a Lambda. In the bottom one, we have a Lambda. In the middle one, we have an EC2 instance, which is hosting a service. So that's a designated set of EC2 instances. Regardless, API Gateway will invoke the right service, receive the response, and send that response back to CloudFront to then be combined with the front-end static shell that was fetched from S3 and returned to the user. Now, when a given Lambda, let's say the criminal justice reform microservice, is invoked, it will trigger that microservice's Lambda function. That Lambda function, since it has been invoked, will then be spun up on a host somewhere, we don't care, and depending on what code it contains and what data resources it needs, might interact with a relational database in Amazon RDS, a non-relational database in DynamoDB, or just fetch some set of objects that you've stored in Amazon S3. After fetching whatever data it needs, the Lambda or EC2 hosted service will run whatever additional processing or calculations or computations that it needs to, and then will return the results back to the API gateway, which will then send the results back to CloudFront. At that point, the static website content that was fetched from S3 and the dynamic content will be returned in a final HTTP response to the client's web browser. The gray dotted line that you see around all the microservices, that's your VPC. So it's the network, the designated range of IP addresses that AWS resources are deployed into. So things like EC2 instances and RDS clusters will exist within that IP range. Serverless entities like DynamoDB and S3 don't actually exist within your VPC, but they can be configured using security policies so that only things within the VPC can access them. This is all very much simplified, but I hope it gives you a decent idea of how things are tied together in the cloud. Different services are used to do different things, but they are connected to one another as well. Lambdas and services running on EC2 instances can utilize data resources such as RDS and DynamoDB. API gateways can be configured to route service requests to the right Lambdas. S3 can be used to store all your static front-end code. Route 53 can be used to register a domain for your application, so on and so forth. It's all an ecosystem of interconnected services, and there's a lot more services that exist and can plug into this architecture, but going over all of them would take a much longer time. The services we've covered here are very commonly used, and they'll be helpful to illustrate what AWS provides and why it's so important. And again, all of this is in the cloud, which means that your web servers, your application servers, your database servers, your servers to host your static content, none of that is managed on-premise by you or your company. AWS takes care of all of it. You just click a few buttons, pay for what you use. Okay, so we've covered infrastructure as a service, platform as a service, and functions as a service offerings. As we discussed, these are the tools that you will primarily use to build your own software application. So now let's discuss information security. As we've discussed, moving to the cloud has its risks. As opposed to physical servers that are only accessible via a local network that can only be accessed on-site, resources in the cloud can in theory be accessed by anyone, anywhere in the world if they have the relevant credentials. All they need is the internet and some hacker skills. So when you're talking about large banks and other financial institutions, moving to the cloud isn't as clear-cut as it might seem. They must be able to guarantee to their own customers that they can continue to provide the same level of security that they provide with their in-house solutions, which ultimately means that cloud providers themselves need to be able to make the same guarantees. When talking about highly sensitive transactional data, billing information like credit card numbers, or even classified government documents, cloud providers need to provide the systems to ensure that a move to the internet-accessible cloud isn't jeopardizing the sanctity and privacy of the information that's being stored there. AWS, as a cloud services provider, provides a range of services for cloud security at the various levels of its architecture. Working from the ground up, at the individual resource level, we're going to start with Identity and Access Management, otherwise known as IAM. AWS IAM policies allow admins to granularly control who is authenticated and authorized to use specific resources. For any given resource in any given service, IAM establishes rules as to what users or what other AWS resources can access a given resource. This is applicable to networks, to databases, to Lambda functions, to S3 buckets, and so on and so forth. So now you can say, for example, that the only entity that should be interacting with the climate change database is the climate change Lambda function. If anyone or anything else tries to access that database, deny them entry. Using something called policy documents, rules can be established for every single resource in your AWS ecosystem. For the data itself, AWS supports the encryption of data both at rest and in transit. It has another service called KMS, which stands for a Key Management Service, which makes it easy to create, manage, and distribute the private keys that are created for encrypting and decrypting data. In this way, even if someone were to somehow bypass IAM and get access to the client management system, all they would see is a bunch of encrypted gibberish. Moving one layer up, as we discussed before, the VPC provides network security. By attaching IAM policies to your subnets, you can specify exactly who and what is allowed into the network. You can visualize this as the first layer of defense, the fence around your house. Auditing and logging are also provided as free services to AWS users. Let's say some confidential files that were stored in S3 were leaked to the public, and you need to get to the bottom of who is behind it. With AWS CloudTrail and AWS CloudWatch, you can root cause exactly who accessed that S3 bucket and when. The two services combined provide a clear record of activity on all your AWS services in the case of a security breach. On top of this, built-in security wizards like Amazon Inspector run in the background of all your AWS operations and analyze a given AWS ecosystem for security risks and vulnerabilities that might impact security and compliance. Let's say you accidentally left your internal databases in a public subnet, for example, wide open to the internet as long as someone has the right endpoint. Amazon Inspector will probably flag that and let you know about it very quickly. And finally, in the case that your services do experience an actual attack, AWS Shield provides 24/7 support to deal with those attacks and help you get past them. Another thing to note is that the availability zones themselves, where the data centers are actually hosted, are also probably some of the most secure places on Earth. They have 24/7 security and many safeguards in place to ensure that no one gets access to the physical servers that constitute the cloud. Overall, AWS is really, really secure. It depends on a mutual understanding and a shared responsibility between itself and the user. So AWS will take responsibility for the security of the physical hardware as well as the network. The user will take responsibility for the security of the application and the data, ensuring that the proper IAM, authentication, and authorization and encryption policies are in place to safeguard all resources. Assuming that shared responsibility is being respected, there's almost no reason to worry when using the cloud. So in addition to everything we've already talked about, AWS does offer its own set of SaaS applications. These services won't be used in your development process at all, but can be used for other business needs. Some examples include Amazon Chime, which enables online video meetings, calls, and chats across devices, Amazon WorkDocs, which is a file storage and sharing service, and Amazon WorkMail, which is a business email service with calendaring features. So this is just to highlight that AWS also provides its own SaaS products in addition to the PaaS, FaaS, and infrastructure as a service offerings that it has. And going even further, AWS has so much more. It offers many other PaaS tools, some which we'll cover in the next class, and a suite of over 200 unique services. Some more niche services include Sumerian, which is a VR service, the Quantum Ledger database service, which is a blockchain database service, Amazon Rekognition, which is an image analysis service. At the end of the day, though, the thing to always remember is that all services either use provisioned instances that are dedicated to whatever it is you're using, or they're completely serverless, which means that they don't run on dedicated machines and where they live is kept hidden from the user. Finally, all services are accessed through the AWS Management Console, which is a browser-based user interface for AWS used to manage all AWS resources. That's initial configuration, monitoring, maintenance, interaction, all of it. That's where all the screenshots of the configurations were from. So whether you want to provision a new EC2 instance, upload a new Lambda function, create and interact with your relational database, or add and delete contents to your S3 bucket, it can all happen through the AWS Management Console, which makes AWS super easy to use. And here's what the homepage of the Management Console looks like. So you can see the list of services, you'd click into one and see all your resources associated with that service, and then be able to interact with the existing resources or create new ones within that window. Okay, so this is the last topic we're going to cover, and that's billing, because at the end of the day, the cloud's value proposition involves its pricing schemes. In short, AWS offers a pay-as-you-go model for its cloud services, either on a per hour or per second basis. You only pay for the individual services you need for as long as they are used, without required long-term contracts or complex licensing. So if you want to visualize it, AWS pricing is similar to how you pay for your water and electricity. If you use a lot, you pay more. If you don't, you pay less. AWS also has a subscription fee that is potentially non-existent if you're using a basic set of services. The AWS free tier allows users the use of up to 60 different AWS services for free, up to a certain usage limit. Free tier is offered in 3 different options: the always free option, the 12 months free option, and the trial option. Otherwise, you have to pay a monthly or an annual fee if you plan on using a lot more than what's offered in the free tier. For most small business use cases, though, the free tier should be good enough. Now, if you compare the costs with an on-premise architecture, you can see the differences. By using cloud computing, you completely remove the need for purchasing physical hardware and the IT costs and training associated with maintaining that hardware. The only thing you need to worry about is a subscription fee, potentially free, and the training to be able to use AWS. I don't have absolute numbers for you that are reliable, especially because the savings really depends on the nature and scale of the application in question. But it should be somewhat obvious that the savings can be quite significant, especially for small businesses when thinking about the percentages. And now let's get back to our graph from earlier and understand it more clearly to really dive into why the savings should be so obvious. Note that this graph only helps us visualize the costs of the hardware itself, not anything related to IT personnel or actual maintenance. So it'll make it even more noticeable. So diving into each line, the dark blue line at the bottom is our total demand for a given application. You can see the Monday through Friday as the first 5 hills, and then Saturday and Sunday as the shorter 2 hills. The peaks of each hill are around lunchtime, when request volumes typically max out in a given day, and the troughs are typically at 2 to 3 a.m., when the request volumes are typically at their lowest. The red line at the top is the worst case scenario cost-wise, right? That's the on-premise data centers. And remember, the area under each curve is the dollar value associated with it. So if your application sees requests of 100 requests per hour at its peak in a given week, then you need enough total hardware for databases, for services, for storages, for whatever, to satisfy that peak demand, even if you only experience that demand once a day. You probably want to add some padding as well, in case a given week experiences higher than expected volume for some reason. So at those peaks, you'll be over-provisioned, and the rest of the time, you'll be very over-provisioned, and will have no choice but to continue paying for the hosts, even though they're not being used at full capacity. So that's the red line. You have a constant number of hosts. And you pay for them at the peaks, at the troughs, at all times, because you're paying to rent them and to use them. In the yellow line, you have instead provisioned a certain number of EC2 instances in the cloud. You set a baseline that provisions a given number of hosts based on each day of the week, including weekends. So on Monday, you might have 7 hosts, Tuesday 7, Wednesday 9, Thursday 6, Friday 7. This is an example of scalability in the cloud. Then you have configuration in place so that EC2 can automatically scale up your instances when demand is spiking. This is an example of elasticity in the cloud. So now, instead of a constant number of servers on any given day, you also have some elasticity to scale up as needed during peak traffic. So in the yellow line, you can see the spend has a lower baseline than the red, but can also be increased at certain times when demand spikes. More flexibility than the red line, and less cost, but still not ideal. Finally, in the light blue line, we have a completely serverless model. You don't have any dedicated hosts. You're using a serverless database engine like Dynamo or Amazon or Aurora with a set of Lambda functions and S3 buckets and nothing more than that. Now, all the instances that you need are provisioned in the background only when they're needed as requests come in. So your costs are very close to the actual demand. You can see that the serverless model, if attainable, is the best option from a cost perspective. It has the smallest area underneath its curve. But even if that's not in the cards for your application, simply migrating the EC2 instances saves you money through the principles of elasticity and scalability. And again, this doesn't capture all the cost savings in terms of not needing an IT team, maintenance costs, etc. So moving to the cloud, assuming you can ensure your security needs, is a no-brainer in my opinion in most use cases. So zooming out a little bit, looking at some of the high-level benefits of using AWS. One, it's easy to use. AWS is designed to allow application providers and vendors to quickly and securely host their application, whether an existing application or a new SaaS-based application. You can use the AWS Management Console or a few other well-documented methods to access AWS's application hosting platform. Two, it's flexible. AWS enables you to select the operating system, programming language, web application platform, database, and other services that you need. With AWS, you receive a virtual environment that lets you load the software and services your application requires. This eases the migration process for existing applications you're moving to the cloud while preserving options for building new solutions. Three, it's cost effective. You only pay for the compute power, storage, and other resources that you use with no long-term contracts or upfront commitments. Four, it's reliable. With AWS, you take advantage of a scalable, reliable, and secure global computing infrastructure, the virtual backbone of Amazon.com's multi-billion-dollar online business that has been honed for over a decade. Next, it's scalable and it's high performant. Using AWS tools, your application can scale up or down based on demand. Backed by Amazon's massive infrastructure, you have access to compute and storage resources when you need them, as you need them. It's secure. AWS utilizes an end-to-end approach to secure and harden the infrastructure, including physical, operational, and software measures. In the cloud computing ecosystem, AWS competes primarily with Microsoft, Google, and IBM in the public IaaS and PaaS market. Figures from Statistica show that AWS currently has a market share of 47.8% in the infrastructure as a service sector, along with a share of 25.2% in the platform as a service arena. Contino's 2020 research report, the state of the public cloud in the enterprise, shows again that a whopping 64% of enterprises who are in the cloud in some capacity use AWS for some reason or another. My old team at Amazon obviously used it, and my new team, not at Amazon, is also using it. I would highly recommend it as a cloud provider if you're looking for a place to start. So, to recap this class, we first started talking about how everything we've talked about so far needs to live physically on servers. We then differentiated between having those servers live on-premise versus living in the cloud. We then defined the basic tenets of the cloud and what guarantees it makes to support and enable its offerings. We then covered the 4 different service offerings that cloud vendors can provide: SaaS, pre-built software that lives in the cloud like Gmail; PaaS, pre-built tools that live in the cloud, like DBMSs, IaaS, infrastructure as a service that lives in the cloud, we're including raw servers themselves and networking, and FaaS, which is serverless functions for your microservice suite that live in the cloud. We then took a deep dive into one specific cloud vendor, Amazon Web Services. We looked at some of its basic service offerings, tenets on which it operates, and how it guarantees information security, and how it's priced. So that's the cloud. In the next class, we're going to discuss a different angle of everything we've discussed so far, and that's the process of building software. See you there, and thank you.